In this lecture, we continue our discussion on compressible flow, where we look in a more detailed manner on shock waves and in specific normal shocks. So, in the previous lecture, we were discussing about characteristics and then we were discussing about finite waves. And if you recall, we said that finite compression waves can lead to shocks, and we were trying to represent the motion of a finite wave in the x-t plane, which is a very convenient exercise when it is a one dimensional flow, because the displacement of the wave takes place only along the x direction, and we can follow the wave both in space and time when we make a x-t plot. Just for recollection, we said that a very small amplitude pressure wave which we called as sound wave, when it propagates through the medium, the ripple that is created in the flow properties traverses through the domain at constant speed, that is at the sonic speed, and the wave form remains undistorted as it traverses through the medium. We said that these lines are the characteristic lines. And we see these characteristic lines in wave propagation problems. In a mathematical sense, they belong to the family of hyperbolic partial differential equations. We said that characteristics can be moving either along the positive x direction or the negative x direction, and therefore, there are two families of characteristics which are possible. So, the ones which are moving towards the positive x direction may be called as right running characteristics, and those running to the left could be called as left running characteristics. Based on the characteristics approach, we have the so called method of characteristics, abbreviated as MOC, as one of the very powerful methods for computing inviscid compressible flows. So, if the flow is irrotational, then it is slightly easier to implement the MOC technique, but even if it is rotational, you do have a rotational form of the MOC technique as well. When the wave becomes a stronger wave, then the characteristics can interact. In the case of weaker waves, the characteristics are going to travel through the medium independent of each other, and then all of them are going to travel at the same speed. While for stronger pressure waves, characteristics can interact. And since in this lecture we are going to look at shock waves, let us revisit the nature of the characteristics when we look at shock wave formation. So, we are marking the shock formation with a red line, and we are seeing that characteristics are interacting with each other, forming the shock wave. When do they interact, forming a shock wave? When characteristics of the same family merge together. Why are they merging? Because different characteristics are moving with different speeds. These are the comparatively faster moving characteristics, and these are the slower ones. When we talk about strong pressure waves, the presence of high pressure gradients within the flow also induce a flow velocity in the bulk sense, and in such a situation the dx dt of the characteristic waves are not only influenced by the value of A, that is the sonic speed, but also by the local flow velocity. And the local flow velocity is certainly a function of x and t. For strong pressure waves, even A can be a function of x and t. Now, if you were to look at the nature of the velocity, then you may have a variation like this. And you will find that the variation becomes sharper as you move in time, and once the shock forms, then there is a real sharp change. So, that is how from a comparatively smoother variation you have a sharp change in the form of a shock formation. So, the wave front changes its shape as the wave propagates. In space and time for a strong pressure wave. These are often called as nonlinear waves. When can shock occur in nature or in engineering applications? Let us think about a few examples where in particular we have a special kind of a shock which is called as a normal shock. Normal shock is by and large a one dimensional shock structure. Like you are seeing here in this case, there is a sharp change. What changes about it? It is essentially the variation of the flow property. So, if it was a velocity distribution u, then there is a sharp change in u about the shock. That means, only one component of velocity has changed here, it is the u component. Thereby, we are talking about a one dimensional flow associated with normal shock. So, the flow across a normal shock is basically one dimensional. Where can normal shocks occur? If we try to answer that question, let us imagine a cylinder with a piston and air ahead of the piston, and then you are moving the piston very rapidly towards the right. If the compression is really very huge ahead of the piston, that can lead to shock formation. If you have a supersonic flow approaching a flat surface, there could be a shock formation ahead of the flat surface. If you have a flow through a converging diverging duct or a nozzle, and you are expanding a high pressure gas through this duct, if the flow accelerates from a subsonic condition to a sonic condition at the smallest cross sectional area, which we call as the throat, and then it turns supersonic beyond the throat. If it is not able to adjust with the pressure which is lying outside the nozzle, which we call as the back pressure, and the back pressure happens to be higher than the pressure that is existing in the flow here in the supersonic portion, then a shock may be formed here in the diverging portion of the nozzle, so that the flow is able to adjust with this back pressure before mixing with the ambient. So, these are instances of normal shocks. Why at all is a normal shock formed? From a molecular motion perspective, we have tried explaining it earlier from the characteristics point of view. Now, let us try to explain it from the microscopic point of view, that is through the molecular motions. So, molecules are moving around in the gas, and when the flow is approaching the solid wall here, the flow is reaching the wall and the molecules are colliding with the wall, and then they are colliding with their neighbors and trying to percolate this information all around that there is a wall. This is happening because increasing number of molecules are impacting with the wall, colliding with the wall, and thereby feeling the presence of the wall, they collide back with their neighbors, trying to propagate this information upstream that there is an obstruction. At what speed does that information propagate upstream? It propagates at the speed of sound, the sonic speed. At what velocity is the flow approaching the wall? It is propagating at more than sonic velocity, because you have m greater than 1, and by definition m is v by a. So, what happens effectively is that though these molecular collisions are propagating upstream, trying to spread the information through these disturbances, they do not manage to go far upstream, because the incoming flow is higher than the sonic speed. The sonic speed is not sufficient for the disturbances to propagate far upstream, and therefore, at some point there is accumulation of disturbances forming the shock. And because of the geometric nature of the wall, the shock has a flat structure, which we are calling as a normal shock. In this situation too, the moving surface which is creating the compression is flat in nature, and therefore, the high pressure front which finally forms a shock wave ahead of it also has a flat nature, which is again a normal shock. So, In nature, we also observe shocks which are tilted to the flow direction. Those are called as oblique shocks. We will deal with them in due course. Let us try to look at a one dimensional control volume, and let us imagine that a normal shock lies within this one dimensional control volume. We will say that the flow is approaching from the left to the right. This is the flow direction. This is the normal shock, which is actually a very, very thin region. Typically in air at standard conditions, it is as thin as of the order of 10 to the power of minus 5 centimeters. So, when the flow approaches the normal shock, it has some accompanying properties. Let us say the velocity is u1, pressure is p1, density is rho 1, temperature is T1, internal energy in specific sense is E1, and so on. You can further say enthalpy and other properties including entropy. And then after the flow crosses the normal shock, let us define the properties like this. And let us try to figure out that by applying the conservation laws, how can we connect these sets of properties across the control volume. So, for that we will recall our conservation laws and we will apply them in an integral form. So, we remember that there are finite changes which are occurring across the control volume in place of infinitesimal or differential changes which occurred in the case of a sound wave. You would recall that in the case of sound waves, we had shown the differences in differential amount form, while here the changes are finite. Let us try to write down the continuity equation in integral form, and of course, we will make certain approximations. Let us say we are looking at steady flow, in which case the time derivative term will go away from the equation and there will be only one term left, which when applied to this control volume will be in this form: A times rho 1 u 1 equal to A times rho 2 u 2. It is because the cross sectional area does not have any variation across those stations 1 and 2. Let us call these as stations 1 and 2. So, what we are trying to say is A 1 is equal to A 2 is equal to A. Therefore, the area term cancels out and we are left with the continuity equation in this form. So, this is the mass conservation across a normal shock. What about the momentum equation? Since we are talking about a one dimensional flow, therefore, it is sufficient if we look at say the x component of the momentum equation, and when we do that, the integral form of the equation will contain two terms on the two sides of the equation. This is the advection term, and we are going to have the pressure term on the other side of the equation. So, what all other terms are we neglecting? The time dependent term is neglected because we are assuming a steady flow. Then we are assuming it to be an inviscid flow. So, viscous terms on the right hand side of the equation will not be there, plus there are no body forces. So, these are the approximations that we are doing. That means, we are essentially talking about inviscid compressible flow across a normal shock. additionally this inviscid flow is a steady flow plus there are no body forces. Now, if you try to integrate this equation over the control volume, you will get contributions of pressure and advection coming up in this form, which essentially means that the summation of pressure and rho u square is conserved across the normal shock. So, this is the continuity equation, this is the momentum conservation equation. You are left with the energy equations. So, what will the energy equation look like? Let us include the volumetric heating term in the beginning, we will drop it out later on, saying that we have an adiabatic flow, but in the beginning we retain it. So, these are the terms we have in the energy conservation equation. So, when you apply it to the one dimensional control volume, what would you get? Let us try to write down the equation. Because we are neglecting heat transfer, why? Because we are not putting heat from outside into the control volume, neither are we extracting heat from there. In that case, the heat transfer term will go and then you will only have contributions coming from the remaining two terms, and you will find that across the one dimensional control volume, this is the equation which you end up getting. Also remember that what this equation is saying is that the sum of the static enthalpy and the dynamic part is constant, which means stagnation enthalpy is conserved. Now, these are the equations governing passage of a flow through a normal shock. Now, if you look at these three equations, you will have 4 unknowns to solve, which means these 3 equations are not sufficient. So, what are the 4 unknowns? You have density, velocity, pressure and enthalpy. So, we are missing out some equations. Let us assume a calorically perfect gas. We have discussed about this calorically perfect gas situation in an earlier lecture. So, you know that the equation of state comes in and the thermodynamic relation comes in, thereby you have 2 more equations. Now, what are the unknowns? There is only one more unknown which has joined, making the list now as 5 unknowns. So, additionally you have temperature as an unknown, but you have equal number of equations and therefore, this system can be solved so that you can obtain density, velocity, pressure, enthalpy and temperature, and which is possible algebraically. So, we discussed briefly about the application of conservation laws to a one dimensional control volume, and thereby we came up with the equations which are going to be applicable for a normal shock. So, let us revisit some of the points which we have already discussed over here, that the normal shock is a one dimensional shock and it is a very, very thin layer, and there are discontinuous jumps of certain flow properties across the normal shock, which we will see later on through some equations also. Again, certain flow properties and fluxes remain conserved across a normal shock. For example, you have seen that the product rho u remains constant, that is your continuity equation. The sum of pressure plus rho u square that remains constant across a normal shock, plus h plus u square by 2, which is h naught, that also remains constant across a normal shock. So, that is what we mean by saying that certain fluxes remain conserved across a normal shock. But again, there are certain flow properties which would jump abruptly across the normal shock, which we saw it from the point of view of the characteristics. We would also see it when we handle these equations, and we will find that there are abrupt jumps in properties, and this happens to be a very strong pressure wave, which is formed when a large number of weaker pressure waves they agglomerate. And we have cited different examples here: cylinder within which piston is moving rapidly near the nose region of blunt objects in supersonic flow, and expansion of high pressure gas inside converging diverging nozzles or ducts. Well, you could have other types of shocks. We just said that we could have oblique shocks. So, when does that happen? When a supersonic flow is turned into itself, that is when it encounters a corner across which the body surface tilts upwards to the flow direction, it leads to formation of an oblique shock. So, such a corner is often called as a compression corner, because it compresses the flow and raises its pressure and decelerates the flow through the oblique shock formation. So, we will make a very small sketch over here to explain what we mean by a compression corner. This is how it looks. You have an approaching supersonic flow from the left, and then there is a shock formation right at the corner. So, you can probably look at the problem like this, that the characteristics upstream of the shock look like this, the ones which are downstream of the shock may look like this, and then they are merging into the shock structure. So, this is how one can look at that as a compression wave formed at the compression corner, which raises the pressure and it decelerates the flow as well through the formation of oblique shock. Remember that this shock is not normal to the flow direction, it is tilted at some angle. The flow field as a consequence across the oblique shock will become two dimensional. That means, it will have the u component of velocity as well as v component of velocity. Anyway, if you consider this to be an inviscid flow, inviscid potential flow in a compressible sense, then what happens is that the flow has to remain tangential to the tilted surface, and therefore, if you vectorially sum up these components, then you have the resultant velocity which should lie parallel to the wall. And in order to make that happen, the oblique shock formation takes place, whereby the v component of velocity is induced into the flow, thereby making it two dimensional in nature. And oblique shock is weaker than a normal shock formed at the same free stream Mach number. So, this is an oblique shock which is weaker, but it is two dimensional in nature, and there is an opposite phenomena happening leading to formation of expansion fan when a supersonic flow crosses a corner where the flow is turning away from itself. Why is it turning that way? It is because the body surface tilts away from the flow direction. So, you see that happening here. When the flow turns away from itself, an expansion fan is formed at the corner. So, we talked about characteristics which are moving further apart from each other in an earlier lecture, and that is precisely what happens here, where an expansion fan forms. So, you can consider these as even the characteristics which are lying within the expansion fan, across which the flow is expanding and is accelerating. Pressure reduces and the flow accelerates as it crosses the expansion fan. Now, this flow happens to be isentropic in nature, and again you can understand that it is going to be two dimensional once it has crossed the expansion fan, because it contains both the u and v velocity components. It is apparent from the figure. Let us discuss about some hypothetical state changes of a compressible flow. We will consider a point in a flow field. Let us suppose that the fluid element instantaneously has crossed this point, and when it crossed this point it had a velocity v. Additionally, let us say its Mach number was m, pressure was p, temperature was T, and so on. Now, it could be traveling at either subsonic or supersonic speed when it is moving across this point P. We are trying to treat it as a hypothetical case or an imaginary case where we try to adiabatically slow down the fluid particle from a supersonic condition to a sonic condition if it is really moving supersonically, or we try to speed it up from a subsonic condition to a sonic condition. So, we are doing a mental exercise basically of hypothetically either slowing it down or speeding it up to Mach 1 condition. Now, as this process takes place, what happens is that the temperature of the fluid would change. Why would it change? Because you know that your stagnation enthalpy is constant for a one dimensional flow through a control volume. So, remember that whether that one dimensional control volume we use for a normal shock is used only for a normal shock or any other finite change, it really does not matter. The basic idea is that as long as the flow remains adiabatic, the stagnation enthalpy remains unaltered, and therefore, even in this case the temperature of the fluid would change because its velocity is changing, and therefore, in the stagnation enthalpy expression this portion will change, and in order to compensate the static enthalpy has to change, and static enthalpy for a calorically perfect gas is linked with temperature, and therefore, the temperature of the gas would change. The new temperature of the fluid particle at this state would be defined as T star. That means, T star corresponds to Mach 1 condition. The speed of the sound at this temperature would be defined as A star, which is under root gamma r T star. Using the above equation, we can define a characteristic Mach number, which is given by m star equal to V by A star. So, this is a hypothetical state change that we talked about in order to bring in a so called characteristic Mach number and a characteristic sonic speed. We can think of another hypothetical state change where the fluid element would cross the same point P with the same velocity V, but this time we imagine that we are slowing down the fluid element irrespective of what velocity it has to a 0 velocity, but not adiabatically, but rather reversible adiabatically, which is called as isentropic. So, we are isentropically slowing it down and bringing it to a halt. So, when it comes to halt, we have a pressure experienced by the fluid particle, which we denote by P naught, and it experiences a temperature which we call as stagnation temperature T naught. So, it reaches a stagnation pressure P naught and stagnation temperature T naught. So, with this we will wrap up this lecture. In this lecture, we talked further about the concept of characteristics and how we can use it to explain the behavior of finite compression waves and how shocks can be explained from that point of view. We further discussed about more details of normal shocks. We also applied the conservation equations for a one dimensional control volume to derive the conditions across a normal shock, and then we started discussing about some hypothetical change of states of a moving fluid particle, where we adiabatically change its state to a sonic state, or we isentropically slow it down to 0 velocity, and therefore, we define the stagnation state. Thank you.